Welcome back again. We were talking about the multiple access different techniques. Out of that we have covered FDMA, and we were discussing the time division multiple access TDMA, and we started that discussion in the last period. Now we will continue on TDMA. So on TDMA we were telling that since a single carrier is given to a single user is given the full resource of the transponder, that is in terms of bandwidth and power, you can operate in the saturating region, and therefore the maximum power you can operate, whereas in case of FDMA you have to operate in linear region because multiple carriers are there, and in nonlinear region that will generate spurious. So that is one of the biggest advantage of TDMA. Now in terms of time interleaved burst that will be transmitted down to the ground, the receiver needs to find the information which the information where it is the information meant for him in the burst. So let us see what are the additional information that has to be sent along with the data. There are, for the receiver, some time will take to properly identify where is properly identify a burst. A demodulator has to identify where is the burst in terms of frequency. So it has to search and find where is the carrier frequency, because the demodulator might be having some VCO frequency or center frequency in free running condition, and suddenly at the input another one carrier has come which may have a slightly different frequency because of various reasons, because these receiver and transmitter and in the intervening thing there may be difference in frequency. So it takes some time. So that time is called carrier recovery time. There are techniques available to how to recover. We are not discussing about the technique right now. Let us see, it takes some time. So that is the additional time. Now then, after finding the carrier, you have to find out where the transition of the bits are occurring. So you have to search and find the transmission bit timing, the bit timing, that was the frequency. This is the bit timing, and synchronize your local bit clock with that recovered clock has to be found. So it is called bit timing recovery. That is the bit timing. To recover the bit time you need some extra time and synchronize to them. So it is called BTR. And then after getting the bits, you do not know exactly where, because you have lost some time. So you do not know exactly where your data starts. So to beginning of the data there is a sync pattern or unique pattern is given. It is called search and find out that unique pattern at the start of the bit stream. Like a frame has a header, so this header is a unique pattern. So the start and detection time of the data start time has to be detected. It is called Unicode detection time. And then in a total frame, when you have to transmit, you have to search and find the burst timing of the network and start of the frame containing the network burst. Say a station is switched on and some TDMA network is running in the transponder. So you should know where that the frame of this at the transponder, the frame where it has started, because if a receiver is looking, he will receive continuously data burst one after another. Now, which data burst is from whom, there has to be identification. So they identify in terms of frame. So timing is given in each frame, some time is given to each station to find out the frame timing. So you have to find the burst clock and the frame synchronization time, and as the different station transmission clock may vary in phase, each station clock timing as well as phase may vary. So when it reaches at the satellite, the bursts may drift this way, that way, jitter. So they should not overlap. So therefore there has to be certain guard time given, just like in terms of FDMA we had given guard band here in frequency, here you have to give some guard time. So these are certain extra times which are required, you can see in a satellite at the transponder, if it is continuously looked, you can see that the TDMA frame with 5 different stations A, B, C, D, E is shown here. There is a reference burst, and then say first burst timing is given to station B, second one for station A, then D, then E and C, like that, and it repeats after that. So there is a frame here, one reference to the beginning of the next reference. This we can call frame. This is being repeated, and each individual burst is having certain guard, that is guard time, that is guard time here. It depends on the jitter of the bursts from each station, their clock jitter, and then each individual station burst has information like carrier recovery time CR, bit timing recovery time BTR, unique word is there, then user station data is there, actual data is sitting here. Similarly, the reference burst, which says that this is the beginning of the frame, may have a CR, BTR, unique word, reference station if it has to transmit data meant for all others in the reference station data. Now these extra things, that is the guard times, and then this is that overhead including the unique word and the reference burst, are not useful bits. They are not the useful bits which are being exchanged. So these are the losses. Let us look at it. The above times can be counted in terms of number of bits in TDMA transmission bit rate. Since these are not actual information bits, but is required for efficient operation of the network, these are called overhead bits. Now CR, BTR, Unicode detection bits or Unicode bits are put together, are called preamble bits for each burst, that is each user burst there are preamble bits. Similarly, there is a reference burst which contains the similar thing. In addition, certain network reference network operation informations are there. So total reference burst are not user burst, user is not exchanging, that is operation for the network, that is also a overhead for the network. Now frame efficiency of the TDMA system can be estimated as eta f, that is frame efficiency, is number of useful bits which is user is exchanging divided by number of possible bits. That means the overhead is our loss in terms of percentage. So it can be expressed as 1 minus overhead bits, number of useful bits is 1 minus overhead bits of the total possible bits in a frame. Okay. Total number of possible bits in a frame is frame time in terms and the TDMA transmission rate. So if a total frame time is known and the TDMA transmission rate is known, then you can find the total number of possible bits, that is the denominator. Let us take some quick examples so that we understand the meaning of each of them. That is, assume in each frame there are 2 reference busts. 2 reference busts are put because in case of one reference bust failure, there is network synchronization failure, people cannot communicate because they don't know where the frame start is. So therefore normally there are 2 reference stations are there who transmits at 2 different locations. So 2 different buses, each reference bus is 76 bits. These are some Intelsat type of TDMA numbers, practical numbers. Preamble for each user burst is 560 bits. Rest of the bits in a user burst is useful bits. This is the preamble bits, that is the overhead bits. So you have reference bus 2 times of reference bits and user preamble n times if there are n users, and guard time equivalent bits are 128 bits. Let us take a 2 millisecond frame time and the efficiency of 95%, and of course the bit rate is 120 megabits per second, that is the transmission rate of the user burst. Okay. So total number of bits can be calculated because the frame time is given and the bit rate is given. So efficiency is, we have seen this expression, 1 minus overhead bits by total possible bits in a frame, and overhead bits are bits in reference burst, total number of preamble bits and total guard time equivalent bits. the efficiency is 0.95, 1 minus 2 times the reference bus, 2 into 576, n times the 560 bits, that is the overhead preamble per burst, and n plus 2 because 2 reference buses are there. So, between reference bus also has to be guard time. So, n plus 2 into 128, and since n users are there, so n user bus, so 128 guard time. So, n plus 2 times the guard bits divided by the bit rate multiplied by the frame time. So, here comes out to be n is equal to 15.3. Obviously, the lower number has to be given. This argument has been explained to you in FDMA. So, 15 users are possible. Let us say if the number of bursts are 12, and then what is the transmission rate? You can find out efficiency is known, 12 bits, and then frame time is given. So, you can find out. So, any number is missing, you can find out those things. Now, when we do the capacity estimate, let us do in terms of here in terms of, let us say, voice circuit. So, actual information rate in a frame is total number of bits in a frame minus overhead bits in a frame divided by frame time. So, information rate in a TDMA, that is TDMA transmission rate minus overhead bits by frame time. For voice circuit, so TDMA information rate and transmission rates are not same. You have to remember that because there is overheads. So, TDMA information rate divided by voice channel bit rate is 64 kilobits normally taken. So, you can take the voice channel number of voice channel. If the voice channel bit rate codecs are used, it can be different. Let us take a quick calculation. That is in a TDMA system, having each burst preamble is 560 bits, similar to last one. Reference bus size is 576 bits, number of reference bus 2, just like last time. Guard time is 128 bits, TDMA transmission rate 96.64, and voice channel rate is 64 kilobits. Number of voice channel you have to find. How do you proceed? That is TDMA info rate, that is information rate. Transmission rate is given. Find out the information rate based on the expression. It comes out to be here in this case 91.8 megabits per second. So, that divided by the voice channel rate here given as 64 kilobits, you get 1434.5 channels. So, the lower number is to be given, 1434 has to be taken as number of channels that can be supported. But the important issue in TDMA is synchronization, particularly the network synchronization. This network of stations, they are sharing the transponder in terms of time. So, they must transmit with the synchronized burst clock. The transmission from station reaches the transponder at a different time. That is the idea. So, that in the frame it has to be put in proper time interleaved. So, this time synchronization among the station is very important. Now, for that, from individual stations, they are at different locations. The range delay is different. The delay from the station to the satellite will be different from each station. The delay comes into play in this case. This can be done by sending and receiving your own burst, or it can be done by detecting the reference Unicode burst. Now, you have to, the TDMA frame has to be synchronized in terms of reference burst, which is at the frame rate, and from that you have to find out the burst clock, and that at that rate the transmission has to take place. Now, to adjust the burst transmit time, this burst must reach the satellite in the next frame at the allotted time slot. So, first you have to detect where is the reference Unicode burst, and based on that you have to transmit, and you should know the range. But exactly the reception of your Unicode burst or the reference burst may not be the same as the allotted burst time. let's look at it the way what I am telling. Let's look at it at an example. Say at the satellite, this is at the satellite, these are the frames. F is standing for frame, and the beginning of the F is the reference burst is appearing. So these are frames. Now at the satellite, some reference frame was some frame is there. The reference burst will be received after a delay, propagation delay p, at a user station. Now from the reference burst at the satellite, it is already allotted that this particular user station after so much time it has to reach. Now since the propagation delay has to be brought into picture, you have to find out that from a reference station reception of the reference burst, after how much time you should transmit. So that calculation is shown here in the form of a picture. So when you receive the reference burst, actually it is time delay is of the order of 125 millisecond, and these frame timings are of the order of 2 millisecond, 4 millisecond, like that. It's very small compared to that. So by the time you receive, couple of frame might have passed, so you don't know where you will be reaching. So only propagation delay is known to you, and then let us assume that you are yourself is a reference burst, you are transmitting. Then with respect to the reference burst, the allotted time t is to you. If you transmit with respect to that reference burst, you will reach the satellite with the propagation delay after reference burst. So if this is m times the frame which your imaginary your reference station, if you are, which will reach the satellite exactly at the reference station reception, at the reference station reception at the satellite, it is the other reference station is transmitting. Now here it is imagined that you are transmitting with respect to that after time t, but this point is not known to you, this time is not known to you with respect to the reception of the reference burst what you have received. This time has to be calculated, but in this we can equate that m time f, m is unknown, m time f could be the propagation delay reception, propagation delay transmission. So 2 times propagation delay and this unknown d and your allotted time t. So this can be equated, m time f is equal to p plus d plus t plus p. So you can reach at the reference burst, and then after t you will reach there. So you can find out d or d plus t, any one of them, but here d is unknown and m is unknown. So you have to do it iteratively. So if you put into expression, the d becomes m time f minus 2 times propagation delay. Propagation delay has to be known to you either by your own ranging experiment or by knowing the satellite position and your position. There may be some error because satellite will be drifting, or the broadcast station based on knowing the satellite drift, it can model and send you at that particular time along with the reference burst what is your propagation delay that you will get. So somehow you have to know the propagation delay part. Then frame time is known to you, so only this small m, that is which is the integer number of frames, and d is unknown. So you have to iterate this, that f is the frame time, p is propagation delay, select m integer such as the t is less than the frame time, and then once you know that burst transmit time t with respect to d is the d plus allotted slot time from the reference burst. So from the reception of reference burst, d plus t is the time when you are transmitting. Let us take a quick example. A station is allotted to start its burst at 1.5 millisecond from the startup reference frame having frame duration of 4 millisecond. Estimated station to satellite propagation delay is 125 millisecond. Find the burst transmit time after reference burst reception at that particular station. So d is m into f minus 2 times propagation delay, and by iteration you go on changing the m so that d becomes less than the propagation delay time. And for d less than 1 frame duration, that is from 4 millisecond, integer m can be taken as a 63 and d comes out to be 2 millisecond. So, your actual transmission time is d and 1.5 millisecond from the reference burst. So, that is 2 plus 1.5 is 3.5 millisecond. Now, this is the network synchronization part, and but in all this process you have to detect the unique word, which tells you where the data bus starts or reference burst data starts. So, detection of the unique word is very important. Unique word is the beginning of a burst where the actual data is there. This is also used to time mark for the reference burst, and this reference time mark per frame is used for burst clock synchronization for the network synchronization part, that is. But your detection of the unique word is important. How it is done? That is, you put the received data and clock it into a shift register, and you know what is the unique word pattern transmitted. It is known to all stations. So, locally generate the unique word and keep in a register and compare this the received pattern with this local unique pattern bit by bit, and you get a unique word detection pulse. Simple, it is mostly known to you. The problem is that what happens if the error occurs? There may be error in the unique word or the data. So, unique word detection depends on the channel bit error rate, and due to error there could be detection miss if it is the error is occurring at the unique word itself, or in the data pattern if due to error one of the portion of the data looks like a unique word, then it is a false detection. So, there are two probabilities, there is a misdetection probability and false detection probability. Both are based on the channel BER, also based on the size of the unique word. Probability of false detection, that can be reduced by reducing a window through which you check, because unique word is not always happening. It is expected after a frame time and the frame size is known to you. So, therefore, you can generate a time window. Once you detect one unique word, you can generate the next unique word detection time window. So, in the data portion, if there is a error and it creates like unique word, you are not looking at it. So, this unique word time is expected because frame duration is known a priori and it is fixed for a network with a known traffic. So, let us put it pictorial, that is received frames containing the reference burst and the user burst going through shift registers going out, and unique words windows are generated. So, let us say you get a unique word in this window. So, after a frame time minus the unique word size, or a slightly size is larger than that, because if there is a if there is some error in your clock. So, better put a extra n bits over that. So, here the other unique word will appear. So, compare the bits only within the time window. So, in between during this time you are not looking for the unique word, because this is supposed to be data, and in the data because of error if some pattern looks like unique word, you are not looking at it. So, you are looking at the location where the unique word is supposed to come, and therefore, your false detection probability can be improved. Now, probability of misdetection of course can be reduced by, if there is one error you can tolerate, if there is two errors you can tolerate, if there are epsilon number of errors you can tolerate, depends on how much tolerance in your system you have. That is, you can put a threshold of error tolerance, and this expression is known to you, that is misdetection probability is 1 minus p, that is probability of detection, and which is with tolerance I is equal to epsilon plus 1 to n, and n is the header size, and the NCI p is the small p is the probability of BER. So, p to the power I 1 minus p to the power n minus I, and the probability of false detection is 1 by 2 to the power n. I is from 0 to epsilon if you have epsilon for tolerance, and NCI. So, based on probability of misdetection, we have reduced the probability of false detection. So, in some cases people do not tolerate the error. So, epsilon is 0. So, this summation has to be 1 to n, that is the header size or uniquode size. In some cases the tolerance is there. So, based on that you can have misdetection probability calculation. So, these two are the important design criteria for the selection of the length of the uniquode, and of course the pattern of the uniquode will depend on the autocorrelation function and cross correlation function, etc. for the uniquode. Since time is up, we will continue our discussion in the next period. For the time being, thank you very much.